everyone. Today we are going to discuss about what is a power factor. Okay, so in this video we will be discussing what are the definitions of power factor. There are two different definitions of power factor. Then what are the different waveforms, voltage and current waveforms, and how we can explain power factor using that different voltage and current waveforms. Okay, then we will discuss about the different types of power. Okay, what is apparent power, what is reactive power, what is real power. So we will discuss that. Then we will discuss about bare analogy of power factor. We will understand power factor in a different way, so that we can understand it a little bit better. Then what is a good power factor and what is a poor power factor? What are the, what is the recommended range for power factor? Okay, then we will discuss real life example, how if in case if the power factor is low. Okay, for example, if the power factor is 0.7, then what is going to be the effect on the power system? Okay, then the impact on energy bills, how it is affecting our energy bills, and how to improve the power factor. Okay, so these are the topics we are going to discuss in this video. So first we will start, what are the definitions of power factor? Okay, so theoretically we know that power factor is what? Power factor is also defined as the cosine of the angle between voltage and current in an AC circuit. What is that? Power factor is also defined as the cosine of the angle between voltage and current in an AC circuit. Okay, so how we can explain that? That will be explained using the waveforms, that we will go to that later. Okay, so when the current and voltage are perfectly in phase, the angle is 0 and the power factor is 1. That is ideal. What do you mean by that? When the current and voltage are perfectly in phase, the angle is 0 and the power factor is 1. That's ideal. So that waveform is this one, the first waveform. You can see this first waveform, voltage and current waveform. Okay, so this in this graph, this x-axis is time, y-axis is voltage and current. Okay, so in this waveform you can see both the current and voltage waveforms are starting from the same point at the same time, 0 at the same time, and they are reaching their peak point at the same time itself. See, this x-axis time, so they are reaching their peak value at the same time, and then again they are coming to 0 at the same time, then again going back to negative at the same time, then coming back to 0 the same time. So that is why they are called what? In phase. So both this voltage and current waveforms are in phase, and this is an ideal case. This is called power factor is equal to 1. When the power factor is equal to 1, the voltage and current waveforms are in phase. This is actually an ideal case. And if your system has resistive load, what is the resistive load? Resistive load means in case of there is only light sources, okay, light fittings connected to a circuit. So that is mostly resistive circuit, not CFL lights, normal LED lamps and all. Okay, that is the resistive circuit. So if your circuit has only resistive load, then the power factor may be equal to 1. So current and voltage waveforms will be similar to this. And at the same time you can see this second waveform. This is for inductive loads. What are inductive loads? Inductive loads means a load which operates under the principle of electromagnetic induction. A load which operates under the principle of electromagnetic induction. Examples are like motor, then CFL lamps. CFL lamps, the ballast. Okay, best example is motor. If your circuit or if your project has a lot of inductive loads, inductive motors, okay, then there is a high probability that your power factor will be lagging. So what does it mean, lagging and leading power factor? So this waveform explains how the current waveform is lagging. How is it? So this red line is the voltage waveform and the black line is the current waveform. Okay, you can see a difference in this waveform, and it is expressed as phi. Okay, so the voltage waveform starts from here. This time, the x-axis is the time and y-axis is voltage and current, and it starts from this point, this 0. Okay, so the magnitude is 0 and the time is also 0, but in this current waveform there is a lag. Current waveform starts from this point, right? So there is a lag, and that is defined as the power factor, cosine angle between current and voltage. And you can see all along this waveform there is a lag in this, that is not in phase. There is a lag. So most of the inductive loads will act like this. Their voltage and current waveforms will act like this. Their magnitudes will differ. The peak value is here, the voltage waveform peak value is here at this time, and the current waveform, the peak value is here. Okay, they both differ. Okay, that is the example for a lagging power factor. So lagging power factor means what? Maybe it is 0.7, then maybe it is 0.8, 0.9. So these are lagging power factor. Okay, then what is that next waveform? Next waveform is leading power factor. Okay, in this leading power factor, current leads the voltage. Current leads the voltage. Current is coming. This current waveform is coming first. Okay, this you can see the magnitude, the peak value of the current and the voltage waveforms are different. See, current waveform is here and the voltage waveform is this one, the red one. Okay, the peak value starts from here itself, and the voltage peak value starts from here. So there is a difference. There is a difference. And that is why this is called leading power factor. So leading power factor is for capacitive loads. Best example is capacitor banks. That is why most of the projects uses capacitor banks. They will connect capacitor bank to the MDB, main distribution board. So that what will happen? The inductive load effect will reduce. So these two loads, capacitive and inductive load, will act together and they will correct it to this in phase waveform, voltage and current in phase waveform. Okay, so the larger this angle, the lower the power factor. So if this angle is larger, this lagging is larger, the lower will be the power factor. When the voltage and current are perfectly aligned, the power factor is 1, like this. The voltage and current are perfectly aligned, the power factor is 1, which means the system is most efficient. Which means the system is most efficient. Okay, so this is the first definition of power factor by using the cosine angle and the waveforms. Okay, and that is a little bit complicated. And how we can understand power factor in a different way. How? The next definition is power factor is the ratio between real power and apparent power. What is that? Power factor is the ratio between real power and apparent power. Real power measured in kilowatts, and that is the actual useful power that does the work, like running a fan or motor. And what is apparent power? Apparent power measured in kilovolt amperes is the total power supplied by the utility. So the power factor equals kilowatts divided by kVA. What is the definition? Power factor is equal to kilowatts divided by kVA. What is kilowatts? That is the real power, and kVA, that is the apparent power. So what is the real power? What is apparent power? How you can understand this? Okay, so that definition I rewrote it here. Power factor is the ratio between real power and apparent power. Power factor is equal to what? Real power, that is kW, divided by kVA. Okay, so kW is equal to kVA into power factor. kW is equal to kilowatt is equal to kVA into power factor, where kW is the real power. This is the actual useful power that does the work, like turning a motor, running a motor. Okay, this is what this power is what we use for doing work, like lighting a bulb, running a motor. Okay, for charging a mobile phone. So these are real power. This is useful power. Okay, then what is the kVAR? There is 3 types of power. Okay, I'm coming into 3 types of power. What is first one is real power. That is useful power that normally we use for doing our work. Okay, and what is the next one? The kVAR, kilovolt ampere reactive. That is reactive power. This power is needed to create magnetic field in motors, transformers, and other inductive devices. This is actually called useless power. We cannot use this power to light a bulb. Okay, then the third one, apparent power, is the total power supplied by the source. So that is the total power available for the project, and that is the total power supplied by the source. What is the source? Maybe it is transformer, or maybe it is a generator, or maybe it is a UPS. That is why these all these systems are expressed. Their ratings are expressed in kilovolt amperes, kVA. So normally the transformer's power rating is expressed in what? kVA, 1500 kVA, or 1600 kVA, or 2000 kVA, 2500 kVA, not in kW. Okay, why? They are expressed in apparent power. That is a source. Also similar to that, that is a generator also expressed in kVA, and also UPS also expressed in kVA, because those are a source, power source, and it is expressed in apparent power, not in kW or real power. Okay, how to understand this? We use Beer analogy of power factor. We use what? Beer analogy of power factor. Okay, in this glass, the total power is actually what? The apparent power. This is the total power supplied to our project. For example, 1500 kVA or 2000 kVA. If there is a transformer whose rating is 2000 kVA, supplied power is what? 2000 kVA. So that is the total power, kVA. And this is the useful power, kW. This is the actual power. Real power, what is that? This is the actual useful power that does the work, like turning a motor. Okay, this is the actual power, real power. And this form, this is called what? Wasted electricity, and that is what? kVAR. So this, we can say kVA is equal to kW plus kVAR. That is a vector sum. Okay, to understand that a little bit easier, in a easier way, so we can say kV is equal to kW plus kVAR. That is a vector sum of kW plus kVAR. kVAR, what is kVAR? Reactive power. This power is needed to create magnetic field in motors, transformers, and other inductive devices. We cannot use this power to light a bulb. Okay, that is wasted electricity. And kVA, what is kVA? That is called apparent power. This is the total power supplied by the source. What is that? That is its total power supplied by the source. Like transformer, power supplied. If the capacity of the transformer is 1500 kVA, that is a total power supplied by the source. Okay, so we move on to the next slide. What is that? Good power factor versus bad power factor, or good versus poor power factor. So what is the ideal case of power factor? Power factor is 1. Power factor of 1 is ideal. What is that? A power factor of 1 is ideal. It means all the supplied power is being used efficiently. So kV is equal to kW. So for example, we have 1500 kVA transformer, and we can use 1500 kW. We can connect 1500 kW load to that transformer. That is an ideal case. So that means the power factor is 1. Okay, and what is the recommended value of power factor? The recommended value of power factor ranges from 0.09 to 0.99. 0.99, 1 is the ideal case. So most of the regulations recommend the power factor should be within the range of 0.9 to 0.99. Okay, so the recommended value is 0.9 to 0.99. Otherwise, you might get a fine from your utility service provider, like DEWA, Dubai Electricity and Water Authority. Okay, a low power factor means your system is drawing more current to the same work. What is that? A low power factor means your system is drawing more power, more current to do the same work. This leads to energy wastage and higher cost. I will explain that in a real life example how that wastage of energy happens. Okay, so we consider an example here. The total connected load here is equal to 100 kW and the power factor is 1. The current drawn is minimum. That is the ideal case. Okay, so apparent power. This is the ideal case. Apparent power is equal to kW. kV is equal to kW divided by power factor. What is the apparent power? kV is equal to kW divided by power factor. Okay, so in this first example, we consider power factor is equal to 1. The second example, we consider power factor is equal to 0.7. And we will see what is the difference we are going to get. Okay, so the real power is equal to real power. P is equal to what? 100 kW. That is the total connected load. So this much load we connected to the system. So real power is equal to 100 kW. Okay, for in this example, power factor is equal to what? Power factor is equal to 1. Okay, so the apparent power is equal to S is equal to kW divided by power factor, that is 100 kW divided by 1, which is equal to 100 kVA. So to run a 100 kW load, we only need 100 kVA power source. What is that? To run 100 kW load, okay, we need only 100 kVA capacity source, like 100 kVA transformer. Okay, we consider second case, power factor is equal to 0.7. So what will happen? Apparent power is equal to real power divided by power factor. So 100 kW divided by power factor, which is approximately equal to what? 143 kVA. So to run this 100 kW load, we need to have a capacity of 143 kVA transformer. We need to have 143 kVA transformer, not 100 kVA. So that is the effect. So if the power factor is very less, then we need 100 kVA as the apparent power. Okay, so but if the power factor is 0.7, the same 100 kilowatt load will draw 143 kilowatt amperes, which increases kVA, means increase in current. So when the kVA increases, obviously the current also will increase. This is directly proportional. So when the kVA increases, capacity of the transformer increases, the current also increases. So which means 143 kVA it will take from the system, and the current also will increase. That is 43% more current. So your energy bills also will increase. Okay, so what is the impact on energy bills? What are the impacts on energy bills? Most household appliances, domestic consumers, uses what? Mostly resistive load and lightly inductive, like lights, TVs, heaters, phone chargers are mostly resistive or lightly inductive. So these loads are very much resistive load, not inductive load. So the power factor in homes usually stays close to 1, not less than 0.9 or not less than 0.94. It will be mostly for homes, it will be mostly because there are no big motors or anything. There will be only very small motor, and most of the other loads are resistive loads. So for domestic consumers, the power factor in homes mostly stays close to 1. But in commercial and industrial consumers, they use large inductive loads like motors, compressors, HVAC systems, welding machines, etc. These loads are significantly lower the power factor, which increases apparent power. So the power factor also will be less because they use inductive loads. The power factor will be less. Okay, which actually, if the power factor is less, the system's efficiency will be less, there will be more energy consumption and there will be more energy bills, and also there is a possibility of getting fine from the utility service provider. Okay, then how to improve power factor? So we can, to improve power factor, we need to add capacitive load to the system. So that can be done by using a capacitor bank and or a synchronous condenser. So mostly in projects related to MEP projects, they use capacitor banks like APFC panels, automatic power factor correction panels. What they will do, they will improve power factor. If the power factor is 0.7, which can improve if they add capacitor bank to the system, we can add power, we can improve the power factor value to maybe 0.9 or 0.95. That is up to how many capacitors you adding to that system. We can improve power factor by using a capacitor bank or synchronous condensers. Okay, so I will summarize the entire video. What is that? The power factor equals real power divided by apparent power. Power factor is equal to what? Power factor is equal to kW divided by kVA. That is real power divided by apparent power. The closer it is to 1, the better. A good power factor reduces losses, saves money, and improves system performance. Okay, so now I will conclude this video. Okay, thank you for watching.